Hello, we are the Group 2 and we will present our project, this centrifugal pumps design and simulation. Objectives. Design and simulate a centrifugal pump with a geometry impeller and bullet that meets specification of the problem. To do this, the physical models governing its operation will be identified. Its dimension will be sketched, it will be modeled in Autodesk Inventor and simulated in StarCCM. Parameters such as generate heat, power, efficiency, and cavitation in water and mineral oil will be evaluated. Finally, the operation and efficiency curve will be constructed, comparing the result with the manufacturer's data. A centrifugal pump is a turbo machine that transforms liquids by converting mechanistic energy into hydraulic energy. It works thanks to an impeller and rotates at high speed side a bullet, generating a centrifugal force that drops the fluid from the center of the impeller up towards the outside, increase its pressure. What is CFD? Computationally fluid dynamics is a branch of fluid mechanics that uses numerical methods and algorithms to analyze and simulate the behavior of fluids. However, the accuracy of these models depends on the correct selection of a turbulence model, refined meshes, and the implementation of realistic boundary conditions. Viscous fluid, the higher the friction loss, it reduces the overall pump efficiency. For the other hand, cavitation is a common problem and occurs when the pressure in certain areas of the impeller drops below the vapor pressure of the fluid, generating vapor barrels that collapse and damage pump components. This phenomenon can cause loss of performance, excessive noise, and mechanical failure. CFD models can predict cavitation formation by analyzing the pressure distribution in the pump. Viscous fluids tend to modify the occurrence of the cavitation, as higher viscosity can delay the formation of vapor bubbles.
For the methodology, first we can find different parameters that are used to make different calculations for the design of the centrifugal pump. For the mesh selections, we have different mesh assumptions. In this case, we choosing polyhedral measures that have less cells, respect for the tetrahedral measures that even though it has more faces, the polyhedral present the same results. And next we have the surface measures that have more cells, the thin measures that have more cells in thin areas, and the last we have Prim's layer measures that have more cells in areas near walls. This measure capture boundary layer effects to optimize Y plus values for turbulence models, improve velocity gradient resolution near walls, ensuring computational efficiency without excessive mesh refinement. Regard the mesh independence, we can find this graph that represents the total head and computational time comparison between three measures: the thin, the normal, and the coarse. For the selection process, it was considered that in the head figure, the mesh with the lowest head RMS error is the normal mesh, while maintaining a reasonable computational cost, respect for the thin and the coarse. This suggests that further refinement does not provide substantial accuracy benefits, but significantly increase computational effort. Now, respect for the liquid parameters for the water and for the oil, it's necessary to calculate the Reynolds numbers with the density, the viscosity, the rotational velocity, that this value is the same for the two fluids, and the diameter of the inlet bump. With this result, we can conclude that these fluids, respect from the analysis for hydraulic pumps, are in the flow regime of turbulence model. For this conclusion, we can use the K epsilon model that it used because it is ideal from highly turbulent flows, such as those in the simulations with Reynolds numbers higher than 10 to the power of 5, to offers a good balance between accuracy and numerical stability, correctly capturing the evolution of turbulence in region from for the walls.
And now for the grid independence test. As we can see in the table, we can analyze the comparison between the different type of meshes. We can see that the three meshes are almost in the same wall Y plus values. These insignificant differences are a good sign because it means that the performance of our simulation won't be affected by changes in the mesh generation. Also, as you can see, in some parts of the impeller, the worldwide plus is higher, specifically in the blade tips and in the external parts of the impeller. This means that these zones will need more computational effort and calculations amount. Now, for the operation curves, we will analyze first the efficiency behavior. As expected, the oil efficiency is lower than the water and the manufacturer ones. Also, we can see that the efficiency is the same in the manufacturer pump and in water in approximately 270 cubic meters per hour. This is an inflection point. As you can see in the graph, the water efficiency is the highest in after this point. Also, we can observe in the table below that the beep point in oil operation is the same as the manufacturer. This is a normal result, but however, the general performance of the pump with oil is worse in every other parameter in this analysis. For the total head analysis, we can see that the oil performance is still the worst. Also, in the graph, we can see an irregular behavior in some parts of the curve. There are many factors that can cause this. It may be due to the interaction of steam bubbles. It can cause loss of pressure inside the pump. It can also be due to the difference between the viscosity magnitudes between water and oil. Also be geometry imperfections in the pump, or even energy losses due to cavitation, as we will see later in another graph. In the other hand, we can see the specific speed in the table below. This is a dimensionless magnitude that indicates, in this case, that the pump entered in classification of axial flow compressor.
Continued with the results and analysis is necessary do a comparisons with the manufacturer data and experimental data. For this reason, I will do a short explanation about the chart. The S asset show the experimental values and the Y asset show the CFT head values. The black line S to equal Y represents perfect agreement between the experimental data and the simulation. The dashed red lines indicate a more or less 10% margin. One point divides beyond this more or less 10% indicate a notable difference between the CFD head and experimental head results. Even so, most values cluster near the ideal line demonstrated acceptable correlation. Comparison with the manufacturer efficiency and the experimental efficiency. In this case, almost on the points Stat 1 remain within the more or less 10% lines, reflecting better accuracy in the efficiency simulation. The proximity of most of the points to the S to equal lines indicated a high correlation between the experimental efficiency and the CFD efficiency values. Analysis of velocity profiles. In this table, the velocity profiles at different flow rates for water and oil can be observed. It can be seen that as the flow rate increases, the velocity also increases according to the schedule shown below. This is because the higher flow rate generates more energy, resulting in a higher velocity. Furthermore, since water is less viscous than oil, it moves at a higher velocity. On the other hand, the region with the highest velocity is the rotating area, where the impeller is located, which is responsible for generating the movement. Near the discharge nozzle, the velocity is very low, which could lead to recirculation of fluid stagnation. This is more precise because you can see the sense of the velocity, but the behavior or explanation is the same as the previous table. However, you can see more detail in this part how the velocity in the impeller decreases when the flow rate increases. In this table, it can be seen that when there is no fluid flowing through the pump, no cavitation occurs, which is theoretically correct. Furthermore, as the flow rate increases, Greater cavitation is observed for both fluids. Water produces more cavitation than oil, which is confirmed by the fact that it has higher vapor pressure at 20 degrees than oil. As shown by the scales, however, the viscosity of the oil is also a factor that explains the cavitation produced. On the other hand, a possible solution will be to reduce the rotational speed.
As seen, the worldwide plus for oil remains nearly constant across all flow rates and predominantly blue, indicating low magnitude and minimal variation. This is due to oil's high viscosity, which reduces wall friction and forms a thicker, more stable boundary layer, limiting turbulent effects. In contrast, water's low viscosity allows higher near wall velocity and thinner boundary layer, leading to greater wall-wide plus variations. There is a clear relationship between flow rate and viscosity in wall-wide plus. As flow rate increases, wall-wide plus rises, but this effect is more pronounced in low viscosity fluids. In highly viscous fluids, energy dissipation and lower friction velocity keep wall-wide plus constantly low. The goal for this project was to design a functional centrifugal pump. We created its geometry, performed CFD simulations, and analyzed wall-wide plus values across different mesh resolutions. We found that optimizing Y plus improves turbulence modeling while balancing computational cost. Finer meshes enhance boundary layer resolution, but the reference mesh provides the best trade-off, ensuring consistent global behavior. We also compare operation curves with manufacturer's data. The pump performs best with water, especially at high flow rates, while oil reduces its efficiency due to its viscosity and density. In terms of head analysis, we observe that concavity shift in water and oil curves is likely due to pressure losses from cavitation, geometric imperfections, and viscosity effects. Overall, CFD simulations accurately predict pump performance within a 10% margin, with minor deviations due to unmodeled factors. Additionally, oil maintains a stable low wall Y plus values due to its high viscosity, while water shows more variation, making it more sensitive to turbulence.